that, and we check if that's a piece of the same archive or another archive, and you are able to recover that. Now, why this isn't as simple as just adding numbers of the packed files and see if that matches the archive? Because that doesn't include headers. If you were to add the value of the packed file inside an archive and just add them all together and see if that matches the file size, you would be still missing quite a few bytes that are attributed to the file header itself. So by attributing all of the data and seeing what's between that, we are able to detect generically any kind of data injection inside the archive itself. And of course, I failed to mention is that unpacked size and compressed size don't really matter for some archivers. You can have that as that's not a given information. So you can't really rely on that. You have to check the data itself. Now, of course, if we have found the corrupted content, we are able to salvage most of it. Now, one of the most useful features of this engine, besides finding hidden data, is pre-processing archives, which protects you from all sorts of exploits. So if you have an SDK for, let's say, WinRAR, and you use Nix engine in front of it, you are sure not to be exploited by something that's not patched by the vendor, because we check the file name length and content, because that was most commonly used to trigger exploits in the archival processors. Because if you have a string that's longer than max path on Windows, you would probably overwrite some buffer and have some sort of an exploit. But recently, that has been fixed in every archival processor except QuickZip, which had such an exploit a few days ago. Now, we look for suspicious compression ratio. In order to check for archive bombs, which are nasty, we check if the compression ratio matches the actual data. So if you have something that's compressed, let's say 1 byte, and it says that when it's decompressed it needs 4 gigabytes of space, that's of course a bogus information. So we check for this kind of attacks, because we found that some archival processes would try to allocate all this data, and since they were unable to, they would either slow down the machine or just break entirely. Now, we check for the extract algorithm requirements. Now, this doesn't need continuous updates from our side. It's just something that generically detects if a piece of information is valid or not. So if for example, for WinRAR, when we said the version 25 is needed to extract this particular file, we generically detect that as a bogus information, so we don't really need to update that and say the latest version is that, everything beyond that is a bogus info. We found that some checks on tampering is possible, which prevents some software vendors from decompressing the archive. If we talk about zip, it has a central directory record and a local one, and if that data doesn't match, then something is off. And the way this works is that some vendors use the central directory information to decompress data and some local. So you can have an archive which is extractable by some programs, but not by others, because they're using different points of reference. Now, of course, there's some stuff you can do to, let's say, the archive splits to, let's say, 20 volumes when it doesn't. We also check for that. We check for, and this is interesting, file entry duplication, because nowhere in the specs it says you cannot have 2 files with the same name and extension in the archive. Yes, the archival programs will not enable you to do that, but nothing stops you from creating such an archive. So if you have a tool that is basically a command line and you set it to, I will overwrite any file I found, so the first file will be overwritten by the second one, which is duplicated. And we do all sorts of header checks just to make sure that everything is according to spec, but not only according to spec, what we have seen that works in the wild as well. Now, for every exploit or vulnerability we find, we provide detailed description with the link to our advisory, which you can read and see how the exploit works. Now, we've come to the demo of our engine. We will test the Nix engine on some of our VSAs, and we will test this on Steganography implementation, and we will show how to recover data. So if you cannot see this, but you have a laptop in front of you, you can go to youtube.com/reversinglabs and see this video better. So first thing we're going to do is we're going to use a couple of files to create a zip archive. So let's do it like this. We're going to compress my good friend here to a zip archive. It doesn't matter which processor you use. Let's say this should work fine. And there we have a zip archive that only contains that particular image. Now, if we use steganography tools we talked about earlier, so one of them, which seems to work best, is Zipit Steganography by Karina John. So if we were to open such a file, which we just created, there. We opened it, and it only has one file. That's my good friend. And we will add a couple more files. So let's add Nix documentation, and let's just add it as a hidden file. And let's add another file, which is, let's say, this malware, which is a configure sample. And by saving changes, we have successfully created an archive which contains hidden content. We can validate this just by opening an archive and see it's only my good friend there. And then we can open the same archive with the program again to see if it's able to reverse the process. So we just open Stego. And as we've seen, there's a visible file called donkey JPEG, and two other hidden files inside an archive. I'm going to show you how that looks like with the hex editor. So the donkey itself is visible, but everything else isn't. So if you look at the end, it only has one particular entry, it's donkey. But if we go in reverse and see this all data, and we can just search from beginning for a PK signature. There's one. This is fake. This is fake. Okay, I think we found it. Yeah. And as we've seen, there is another local header which contains malware.bin. And that particular data is stored just behind the first compressed file, which is donkey, and the central directory. So it's all injected. And let's see how this Stego file is processed with our Nix engine. So here's a couple of parameters. First, we want to scan the archive itself to see what's in it. And as we see, there's a lot of data. So what we found is we only have one reported file. So total number of files is one. That's donkey.zip. But we detected some vulnerabilities. We detected the possible attack due to presence of non-standard header data. That's the extra field modification. The possible vulnerability due to different data in local and central directory entries. And by doing a detailed inspection for steganography content, we found the following. We found a detected file unreported by the archive header. It starts at that particular offset. We can go there in the hex editor and see how it looks like.